So welcome everyone, good afternoon, and thanks for your patience. It took a while to get everything technically working, but now everything is up, so we can start. So this lecture is going to be about data or data use in the remote sensing of atmospheric data. I am Sander Houweling. I'm a professor at the Earth Science Department of the Vrije Universiteit in Amsterdam. And I have a research team working on this topic, and I gladly explain you about the kind of things that we are doing, hoping that you would learn something from that. Now you know who I am, but I have no clue who you are, which is not entirely unimportant for the way that I will be explaining things. And that's why I have a Mentimeter, and I will ask if the Mentimeter can start now. Yeah. And with the QR code first, because you need the QR code on your telephone to get into this. So hang on, the browser is going to show you the QR code. Yes. So if you take your telephone and scan the QR code, then you will enter the Mentimeter. Give you a couple of seconds to do that. Yes, I think most people seem to have that. Okay, great. Then we can go to question 1. And so if you can quickly fill in this question, does it work or not? Oh, you still want the QR? Or oh, can you go back to the QR 1 second? This one. Oh, it should be big enough. You're done now? All right, so then you can go to question 1. Yeah, no, you see a different question. How can that be? Is it working now? All right, so yeah, because now it's presenting. Yeah, so all right. Okay, so just go a little, like who you have in the room, so you can. All right, so thanks. That's going well. So that gives me a nice impression that it's a bit a mix of everything, and I gladly took some time introducing stuff. So that is going to be all right. So can you switch now to the presentation? Full screen. Yeah, so then this should move now to the next. Where should I point to get this moving? Yeah, but this computer is not connected. His computer is connected. Yeah, so that's the funny solution to this problem. All right. So what if I say when I want to change slide? All right. Okay. Let me see if. All right. This may be it. Sorry. No, it should be this way. No. Oh. Yeah, it's just the distance between me and the computer, I think. So what if I just say next slide or so that somebody? Right, well, there'll be clicks in the slide. All right, okay, hang on. So the reason for having this talk is that a growing number of data is going down, and this is going really quick. And well, something is going up here, which is the launch of METHOP Next Generation, actually over the summer. This happened, but there is more. So if you can do a couple of clicks, Yeah, so here you see satellites that have been launched over the summer on the atmospheric composition. And well, unfortunately, there's another one in red. That is MethaneSat. It was only half a year in the orbit and then it already failed. So it's not only new data coming in, but there's also things going wrong. But anyway, net, there's a tremendous gain in the number of data that are going down. And just to give you an impression, here is the data rate of Sentinel-5, which is an instrument on board of the satellite that's being launched here. And that is 20 megabits per second. Now you might think your internet connection you would have in home would easily deal with 20 megabits per second. On the other hand, like this is per second, no? And so this is going to quickly add up to something big. And this is only one instrument on this platform. There are more instruments on that platform, and there are many satellites. So the bottom line is the huge amount of data. And now the question is like, how can we make efficiently use of all that data that's being archived? And so that's what this talk is going to be about. Next slide. All right, so first I go through a number of application areas for atmospheric satellite data use. And maybe the most familiar one to you is weather forecasting. You're all familiar with weather forecasting. You just take for granted that we can forecast the weather of the next day. But what is under the hood is a model that has all the dynamic equations of the atmospheric motion. And if it progresses in time, it will start to deviate more and more from reality. So we need to keep it on track. And the keeping on track thing requires a lot of data. And more of that data is coming down from satellites and being incorporated, ingested somehow in this weather forecasting model, which to keep it on track. So next slide. Not only weather forecasting, but in a similar spirit, you can do these similar things also on atmospheric composition. So there are compounds in the atmosphere related to air quality, for example, that can be monitored in this way. The example shown here is from the CRIS instrument measuring ozone in the atmosphere. I won't go into what ozone is exactly. You have probably some idea of that this is a reactive gas that's harmful to humans when it's at ground level. So it generates a lot of data. You have this model which actually has a lot of information about atmospheric chemistry encoded, but also it tends to deviate from the truth. And so if you feed it with data, so you have on the left the data, in the middle the control run of the model, and then to the right, if you assimilate this data into that model, you see that it resembles much more the initial data. You might wonder, oh, well, now we have a model that actually replicates the measurement. So what's the big deal? Why would we do that? The advantage is if a model has this picture of reality, then it also has data at points where the instrument actually has measurement gaps. You can easily gap fill because the model will compute this everywhere, including nighttime and times when the satellite cannot measure, including actually related gases that through the chemistry are related to a compound, and those gases might not be observable. So the model can generate you results that are consistent with the ozone observations, but of observables that cannot be measured this way. One example is OH, the cleansing agent, a radical in the atmosphere which everybody wants to know about. And the hope is that if we tune the model, we get a more accurate prediction on something that is not observable. Another thing more related to weather forecasting is that you now can also do air quality forecasting in this way. So suppose your model is improved by the data, you can run it in a forecast mode and predict the air quality a couple of days from now. And so you can warn people that who have asthma, for example, that they have to be careful in the coming days about what's going to happen. All right, next slide. Another example is measuring aerosols. So aerosols are important for climate, and because they can be a climate coolant. And so a lot of data again are coming down about aerosols. The example here is polar aerosol optical density, so a measure of the amount of aerosol. And top left is the model, and how the model actually deviates from those measurements. So you see the model measurement difference is blue, so it's negative, meaning that the model underestimates AOD that is observed. And then in some kind of an optimization process, actually, we improve the model, put it in the direction of the data. And then you see on the bottom right that the model has come much closer to the data. And of course, if you have that, then what you can do, you take that model to make improved predictions of the cooling effect of aerosols in the atmosphere, which goes into all kinds of climate studies. Next slide. My final example here is the one that I'm most familiar with, is to measure greenhouse gases in the atmosphere. And one reason why I want to do that is not because we are so interested in the concentration of greenhouse gases in the atmosphere itself, because we know that already pretty well. And since many of these gases are quite evenly distributed over the atmosphere, you probably would need a satellite to know the average level of methane or CO2 in the atmosphere. But what we are interested in is to turn that kind of information into information of the underlying emissions. Can we actually estimate emissions from atmospheric concentration measurements? And of course, emissions are really very useful. We want to know where is CO2 coming from, who is emitting that, and can we have some independent control on where it's coming from? And so that's why we like to do that. An example on the right is what comes out of such an analysis, is a difference between the 2020 and 2019 emissions in methane. And the reason it shows 2020, this has to do with COVID. And the COVID year, surprisingly enough, in methane, was not a reduction in emissions, but was an enhancement in the concentration. So somehow the methane emissions went up. And we would like to know where they came from. And so a priori in the top right is just the inventories, our prediction of the difference between the years. And that's almost nothing. Like there was not much expectation on what would change. However, if we feed the data, the satellite data, bottom right, and we see actually a broad enhancement of methane emissions in the tropics. So this gives a clue of what was going on in that anomaly that we don't understand. And so, yeah, so which is very useful for various reasons. Next slide. All right, so now let's dive into this. Like how does this work? This fusion of data and models. For the example first of weather forecasting. So the schematic shows you the dynamical equations of the model that makes a forecast. And this forecast is now going to be confronted with measurements in a kind of a model optimization step that we'll look at next. And these measurements are going to steer the forecast in the direction of the actual observed truth. And that we call the analysis. It's like an adjustment of the state in the direction of the truth. That state is going to be fed into the dynamical model again, which uses it to propagate in time to make the next forecast. Important in this case to know is that we are not really improving the model in the sense that the underlying physics and the underlying parameters of the model are not being adjusted. It's just the state that's computed, which is being updated. So you might think over time, if there is a systematic difference between model and measurements, you should be able to use that information to really improve the underlying model. But this is usually not done in the weather forecasting cycle. There are other ways to do it, but not commonly in this method. Next slide. So if you would want to use data to really improve your model, then there are other methods, and one example of it is something that we call inverse modeling. So in the case of inverse modeling, the schematic looks a little different. You have the dynamic equations that give you a forecast. And again, there is this minimization, optimization against observations, but now it is not, say, the observable that is going to be adjusted. It's going to be a model parameter, which is related to the observable, which is going to be adjusted. And as an example here, you can take the greenhouse gas case, where we have the emissions here, the concentrations there, and to tweak the observations or the measurements of CO2 or methane in the direction of the observations, we tweak the emissions. So we don't optimize the concentrations themselves, but we optimize a model parameter that is underneath. And that's why when we call it inverse modeling. And you might wonder where this name inverse modeling comes from. And then we should turn a bit to the mathematics. You see on the top right, there is, suppose B are the data, the measurements, M is your model. Then in say a forward mode, what happens is you just project the X, your uncertain emissions, your model parameters. You have this operator which translates emissions into concentrations. So that's what this equation says. D observations is a multiplication of a model operator times the emissions. But what we want really is X, the emissions. And what you could do is solve this equation, say, like we rearrange to get X, and then it means you get the inverse of your model. And so this is inverse modeling in a way, what we're doing. But the trouble is that usually you cannot just take the inverse of a model. In those cases, this cannot be done. It's called that way, but we need another method that is approaching that, is doing kind of that without literally taking the inverse of your model, which cannot be done. All right, next step. Next slide. So let's see how now this model optimization thing, how this works. So we start with the same, say, model equation. And now the reason that this x is now within parentheses is this is not necessarily a linear model. Of course, it could be, but not necessarily. If it is linear, then we can change mx into m times x. And honestly, in that case, you could even simplify your model and see it as a matrix multiplication. And you should run your model many times to populate all the entries in the matrix, but you could think of it, of your model, basically as a kind of a matrix operator that is multiplied by your uncertain parameters, x in this case. All right, so next, or click actually to get, yes, further. Because what we are doing to fit the model to the data is to first set up what we call a cost function. Cost in your mind is usually like a cost is a bad thing. If costs are high, then you're unhappy. If costs are low, you're happy. So what we want to do, this cost function, we want to minimize to reduce the cost as much as possible. And there are two terms in the equation. One is a data term, and the other is a parameter term. And we'd like to minimize both. And what that means is that the first term, the data term, is you have measurements here. And if you take the difference between measurements and your model prediction, you want that to be small, because then your model matches the data well. So that's why this term you want to have small. But also the second term is a parameter term, which says actually about your solution that you get out. You also don't want this to be far from a first guess, because then you're drifting a lot away from reality, and that solution may not be realistic at all. So you want a solution that is not far away from independent other knowledge that actually you have on those parameters. So that's measured by that term. You want also that term to be small. So two terms small to minimize the cost function. Click again. So then there are two things left, which are R and B, are covariance matrices determining the weight of every element, measurement element or parameter element. Things you are certain about, you don't want to adjust a lot. Things that are uncertain can be adjusted. And to have a control on that, these weights, you plug in these covariance matrices, R for the measurements and B for the parameters. So then now we've explained everything that's here. Next question is how to minimize this thing. Next slide. So the solution that we're after is called XA. Is the A for analysis or for a posteriori. And that X is basically the parameter that, or the parameter set that minimizes the cost function J. And depending on how that cost function looks, we could have a very broad minimum or a very narrow minimum. And that tells you how well this parameter is constrained by the data. So if it's like this, then it's really well defined and you know pretty certain that it should be within a small margin. This tells you that the uncertainty of this estimate is small. Whereas here, it's much bigger. So the curvature of the cost function at the minimum gives you directly information on the uncertainty of the parameter that you have optimized. Yeah, hopefully that's clear. So then we can go to the next. All right, so now, how do we minimize actually that function? What are ways to do that? An easy way, in the case your model is linear, it works very well, is to use something called the Newton method. If you minimize a function, what you want to do is go to the point where the first derivative is zero. In this minimum, maybe you learned from math, derivative zero is the minimum. So you want to have the first derivative, and you want to know how quickly this derivative is changing if you change x, which is the second derivative. If you take the ratio like that, then this is a method that brings you in the direction of that minimum. Click again. And you can work out the math, I want to do it quickly, not to take too much time. The first derivative of the cost function is this guy. The second derivative of the cost function is that guy, and then click again. And if you do the math of that, then you get to this solution. In case your problem is linear, what you have on the right, the blue curve, is actually a parabola that you want to fit. And then this solution, since you're kind of fitting a parabola, is instantly giving you the right function. So you don't need to iterate actually to get to the minimum. In case of linear problems, you are there instantly. So this is pretty efficiently bringing you to the minimum. The only trouble is that there are big matrices involved in doing this, which can cause that this problem won't fit in your computer. So, and in those cases where this doesn't work really because it's too big, we need to turn to something else. But now I have a clock. I see the clock. There's meant to meet the question 2. Can we turn to that? Yes, this is a question about, so we talked about the minimum, but now how about the uncertainty in that minimum in the case that we just discussed? So what determines that uncertainty? And the question to you, is this going to be the fit of the optimized model to the data, how well this fits? The pros and the a priori chosen uncertainties in B and R of the quality of the dynamical model that you are using. It's interesting to see how this develops. People learn from each other. Or maybe in the wrong direction. It could also happen. Huh? Yeah, so it's kind of equal between the first two, interestingly. The right answer is actually the second one, the middle one. And the reason is, and now we need to go back to the slides, because I need to show you the equation for the uncertainty of the solution. Go back, maybe back one. Yeah, here, yes. So I told you that the curvature of the cost function at the minimum tells you about this a posteriori uncertainty, which is this guy. And if you look what's inside here, it's not a function of the data itself. It's not a function of the model prediction. All that is not in that equation. It only depends on the structure of the model and the weights, the a priori weights you assign to the data and to the model parameter. And so that means if your assumptions on those weights are wrong, then your estimate of uncertainty may actually not reflect the true uncertainty. And that's something always to bear in mind. Somehow you need to confront this uncertainty estimate with some kind of validation to really know if your uncertainty actually is a realistic uncertainty in the first place. All right, so that now we can go to the next slide. Yes. What in case this problem is just not tractable because it's too big? It simply doesn't fit in the computer. You need something else. And one problem can be that the second derivative of the cost function j is actually too big to evaluate. It's a too big problem. Suppose you don't have that. So how do we proceed? And so the method that does that, or a method, is called the variational method. And you find it, for example, in 4D var. That may be a term that you have heard in the past or in literature. What you need for that is be able to evaluate the cost function at a certain set of parameters. So that's the first. And you need to be able to evaluate the first derivative of the cost function at a given point. And once you have that, what you can do is in the bottom right corner, you can use the point and the gradient to move in the right direction iteratively to go in the direction of the minimum. So you do it in several steps. And there are efficient and less efficient methods. And for linear problems, the conjugate gradient method is extremely efficient to do it. But there are other methods too, depending on the problem you have at hand. So this is how this approach works. But there's one interesting tweak to it. And that's going to be in the next click. Because what you need is m times x, which is a forward model run, then you obtain everything you need actually to compute the jx and to compute, well, this component of the first derivative. But there is this other nasty guy, which is the transpose of that matrix, which is, or how do you evaluate that if you just have a model that you can run forward? Next click. This turns out to be mathematically the adjoint of your model. And so you can turn a piece of code into its corresponding adjoint. This is another model, in a way, which is somehow equivalent to your forward model, but it's just coded in a different way so that it generates something that you use to evaluate this. One more click. And so suppose you have this model, this piece of code, we call it MT, then this is transpose of M mathematically, but it's just a model. This takes as input this term, which is basically the remainder, which is here. So, and what it says is the difference between the observations and your forward model run. You put it as input into the adjoint one, and then it's going to evaluate everything you need to determine the gradient of the cost function. And so once you have that, so in the sequence, the way it works is that every time, for every iteration on the bottom right, you first need to run your forward model to calculate that one and to calculate that one. Then you feed that into your adjoint model. You run that. You evaluate J prime, the gradient of the cost function. And these two pieces of information go into the steepest descent or conjugate gradient algorithm to infer the next iteration. And then iteratively you get to the minimum. All right, so next. So suppose now you do not have an adjoint. And because coding an adjoint model is not easy, and if you change your model, you also need to change the adjoint, so this can be kind of cumbersome. There are compilers that ingest your model and spit out the adjoint version of that model. So this does exist, but it's not an easy thing to do. So in case you have a very complicated model, this could be very hard. And so I would say if you have an adjoint, then use it, because then it's very efficient. If you don't have it, then you need something else. And so one way of proceeding in that case is that your problem is big, but you can make it smaller by splitting the observational data set in many chunks. You do it in smaller chunks. You say, well, I have a huge data set, but I split it in 100 pieces. And now, instead of solving this problem at once for all the data, I solve it stepwise for all the chunks of data. So first the first chunk, then the second chunk, and then the third chunk. So then your problem will fit in the memory of your computer, so you can still do it. And it turns out that if you do it sequentially or at once, you can prove that you will find the same solution in case your problem is linear or weakly linear, then the approximation is very good. So this could be a way to proceed. And the method is used Kalman filtering. And now do a next click. So the way this is going to work is it's going to propagate in time, because these data chunks are separated in time. So in the first one, you have the first block with the first set of parameters for that time window and the first set of data. And you use that to optimize, like in an analytical way, the way we discussed initially. Next click. So then once we have that, we take the next chunk of data where, so that one is not only dependent on the parameters in this block, but there could be some propagation of information from these parameters into the next block. They influence the data in the future also. So you also need to take that into account. So the optimized state in the first chunk, the second chunk, is that of the first, plus any new data and new parameters you need for the next period. Next click. So once you have done that, then you enter into the third phase, where now it can be that at that time, these data are not really influenced so much anymore by these parameters. At some point, it just dissipates and loses its information content. So you don't need to consider these anymore, for evaluating this, you only keep the window of parameters that matter. But otherwise, this step is the same as the second step, and this way you sequentially propagate in time. So this can work very well. The only issue and difficulty is the transfer of knowledge from here to there, which needs its covariance matrix to be propagated. And that covariance matrix can be a very ugly beast. And next slide. And so if that is too big to fit in your computer, then you need a different approach to deal with that. And a solution to it is to go to ensemble comma filtering. Next slide. So in regular comma filtering, what is important to store in memory is an estimate, the posterior estimate of your fit, as well as the corresponding covariance matrix, and that you carry over to the next window. Next click. In the case of ensemble comma filtering, you actually don't store this whole, you evaluate this whole BA, but rather you sample it in an ensemble of trials. You do it at random. You just sample not only, this is a 1D case for one parameter, but of course you have a factor of many parameters. So this whole parameter space, you're kind of randomly sampling a number of times to represent the whole covariance structure. And so for this one parameter, you might think like, what is the gain? Because here I have two pieces of information that I need to propagate, and here there are n pieces of information. So you would rather think that the problem gets worse. But if you think of this multidimensionally, then all these random draws are also factors of the many different parameters, and you don't need to sample every parameter so many times, but you just take efficient sampling through the whole space. And in that way, you can save tremendously on the amount of information that you carry in order to represent the entire covariance structure of your problem. And so that can really save you memory. And then in that way, you can solve the whole problem. You need the proper math to translate the problem into a statistical problem that can deal with ensembles, but it can be done. The other big advantage of this is that to run ensemble members on a supercomputer that has thousands of processors is very efficient, because each of these ensemble members can run on another part of your computer in parallel. So for parallel computing, this problem can make very efficient use of your computing resource. Yes, next. So now, finally, I'm glad that with the time that was spent in getting the technology ready, I still have time to also cover the last application. You might think, well, this is all nice, but it sounds a bit old school, no? These are techniques that were developed so many years ago, and of course, they still exist and find many applications, and that's why I go through the hassle of explaining you all that. But now we have gone in a different age where everybody's talking about machine learning and AI. So what do these techniques bring to this problem? Before I start discussing this particular one shown on the screen here, I would like to mention there is another one. If you think of weather forecasting, for example, there are now first publications coming out where people are trying to use machine learning methods to predict weather patterns based on the existing current weather pattern, how it propagates in the future. And it's really amazing to see how well this system works. In some cases, really outcompetes the whole complicated physical dynamical model that people used in the past in a way that's much quicker. So there's indeed a tremendous potential for these kind of techniques to speed up things tremendously and approach the problem in a different way, which we would need to explore further in the future to do things even more efficiently. One example that I would like to show, because in the field of atmospheric composition, you don't find many of these applications yet. And I have the feeling that it's really hard to catch the dynamics of tracer and chemistry transport modeling. I've seen some examples of people who nevertheless, were brave enough to try, but it didn't look all that good. So we are certainly not there yet in the application that would say, do what I discussed in the beginning, that you have this chemical data assimilation globally, ingest all the data globally, and then makes a chemical prediction. We are not there yet, but other applications of machine learning slowly are appearing. And one example I would like to give you here, which is that there are satellites now that can track leaks of natural gas. And it turns out, we were surprised to find out that there are many. Initially, I mean, our expectations was rather low. We thought the satellite would probably not be sensitive enough to see it. And so we would be happy to find one. But to the contrary, it turned out that there were many big leaks to the extent you even wonder, how can this even be possible? There's such a safety risk in such a big natural gas leak, but anyway, it happens. So there are many of these instances, and of course, it's for climate mitigation, we really like to know where they are, because this is a way to, I mean, a low-hanging fruit of tackling the climate problem is go out and at least make sure that these big leaks are fixed. So an example of satellites measuring that, the TOPOMI satellite, the Dutch sensor at relatively low spatial resolution. At the west coast of Turkmenistan, you see these red spots, which are detected natural gas leaks. And then with other instruments, it turns out it's possible to zoom in to really track the facilities on ground. You see some examples here. You can really pinpoint to what facility it is that is doing this. And so this field for observation is evolving really rapidly, but there are also so much data. Suppose that you would want to monitor this globally every day, where the leaks are. Then you need something that's really efficient and fast, processing all the data that are around. And next slide. And my colleagues at Echelon and Leiden, they really were very eager to dive into this to try to make it work. And so they did so. They succeeded. And this map shows you 1 year worth of methane detections of the TOPOMI data. You see many of these spots here, which are leaks that have been found in places. And the way this works is that you use a convolutionary neural network on small images that are extracted from the data. You have many of them. And then the PhD student who did that, he has, of course, you need a training data set with a lot of label data, which is not so easy to get. So he was manually going through many orbits of data you know, this is really slavery work. And I mean, maybe spent a month or more to have a data set big enough of visual identified leaks so that he could train this convolutional neural network. So there is this manual evaluation of everything that comes out, because initially you don't trust it. And the ones you can trust, you can then later feed in and try to use it to improve the convolutional neural network further, and so on. And so that's how this system evolved. However, there are tricky problems with the data that you also need to be careful of. And that's why another thing, it mentions CNN, but also SVC, which stands for support vector classifier. There is another element that you need here. And I'd like to show you why. Can you go to the next slide? So the first step of this machine learning machinery is to do this CNN training. So you try to let the CNN recognize plume-like features, and then and this like works on this manually made data set. And if you apply it, then approximately 0.8% of all the scenes that you check, there is some identification of a plume. Next, click. So, but then you need to know if those identifications are actually true leaks. And the trouble that is encountered is that some of these plume features, they actually are surface albedo anomalies. They have nothing to do with atmospheric plumes. They are just something on the surface that resembles a plume. Or something, in case we have a lot of aerosols in the atmosphere, then the instrument has trouble detecting methane. So there are errors in the retrieval. So the combination of aerosol optical depth and surface albedo is causing trouble in a way that we need to filter out. And for that, we use this support vector classification using aerosol data and surface albedo data as input to classify the data set in a way that you can separate plumes over albedo varying surface from other plumes, and decide which ones can be trusted or not. So that is the second step, and that kicks out scenes. So 45% of the scenes is filtered out that way. They cannot be used. Next click. And this is just to give you some examples of the ones that are kicked out. For example, here is a cloud. There are no data. Huh? And you see here also the cloud fraction. And then there, at the edge of this cloud, there is some methane enhancement. But that has to do with difficulty to separate, say, at the border of clouds, like what is clear sky and what is cloud. So, so this looked like a plume, but it is certainly not. So that has to be filtered out. Another example here is a surface albedo feature you see in the RGB image to the right. It is an elongated feature in the albedo that may look a bit like a plume. And you get a methane enhancement also that looks pretty much like a plume, but this one is not real. It's an artifact. So that one is kicked out too. And if you combine all that in a way that's done by my colleagues at Esfond, then really you can make the system work quite well. Then we go to the next slide. Yeah, which is already my summary. Actually, I did quite well. So I think somewhere we skipped over a Mentimeter question, but maybe it's something worth to discuss about in the discussion. I hope I convinced you that there are many applications that are really important in detecting the atmosphere from space. And to deal with the increasing stream of data, we need these kind of data assimilation techniques to efficiently use the information that is there. I explained to you about Bayesian optimization and all the solutions that exist there to, well, in principle, you might think of this Bayesian problem as something that we know already for so many years how to solve. The problem comes more in the size of the optimization problem that you want to solve, because this is huge. And so the solutions that I've discussed together with you, they are really to make this tractable and make this fit in a computer in an efficient way. And so there are some techniques like 40VAR, ensemble Kalman filter that we went through. And now finally, indeed, like it's curious. And I mean, it would be great if some of you in the room who has an interest in these kind of applications, try out the machine learning approach to these problems and see how far we can push it. So with that, I stop the lecture, and I'm happy to take any questions.